Really excited to talk to you all about this particular topic relating to quantum chemistry, or I'll say quantum mechanics. And one interesting concept we dived into is the theorem of separability, and in here we're going to focus more on this particular Schrödinger's equation, which is H, the operator, which is a Hamiltonian operator applied to not one but two variable wave functions, which is expressed as wave function of x with respect to the wave function of y, or this can be written, I would say, as this with respect to x and the y coordinate to be equal to the energy total, which is the eigenvalue, and this energy total is applied as well to the wave function of x with respect to that of the wave function of y. This is the product, and this is also equivalent to the energy total applied to the wave function of x with respect to that of y. So this is the Schrödinger's equation, and this Schrödinger's equation, we want to be able to show that the theorem of separability, which is targeting this particular wave function, which actually states that we have to treat these variables here, x and y, independently from each other while solving for the operator acting here on this particular eigen function, which is the wave function of x, and also treating the operator with respect to the wave function of y to give us our energy total with respect to the x coordinate wave function and that of the y coordinate in there. So that being said, being able to prove this, we're going to actually isolate the left side of the equation, which is this part right here, and see whether we can actually make the left side to be equal to the right side by proving this theorem of separability. So take note that looking at the left side, we need to be able to look at various terms, or I would say constants, that are known in the theorem of separability. One of it is actually knowing the ifs, which is that if the Hamiltonian operator total is equal to the sum of the coordinate, which is dependent solely on the wave functions, I would say variables, which are the x coordinate and the y coordinate, and also noticing here that since this also can be expressed as the individual Hamiltonian operator with respect to the variables, giving us the energy, which is the Schrödinger's equation for the x coordinate, giving us the energy of the x coordinate, and that of the y coordinate Schrödinger's equation, then we can actually see that we can actually substitute something for another to give us something quite interesting. Now in here, once we look at this, then we just have to go back to this particular expression here and rearrange some specific things right here. So what that results in is noticing that our Hamiltonian operator total to be applied to, I'll say, our wave function with respect to our x and y, and this Hamiltonian total is equivalent to this particular sum. So we just substitute that in here, and what that results in is the Hamiltonian total, which is put in this case as the sum of the x Hamiltonian plus the sum of the y Hamiltonian, and this is going to apply to our wave function on the x with respect to the product of the wave function of the y. Now that being said, since we see this happening, what we then need to do is do a little bit of an expansion. What that means is that I'm going to multiply this first by the x coordinate Hamiltonian operator, and then I expand this with that for the y coordinate, and what I get as a result is this particular expression, which is the Hamiltonian on the x in here applied to this particular wave function right here in terms of the variables, and this is going to be added to the Hamiltonian on the y and multiplied by the y coordinate wave function and that of the x coordinate. And take note that once you notice this actual expression reveals that there is some kind of similarities between the arrangement of the operator with respect to the wave function and this here. So what that results in is that we substitute this here for the energies of the solution, which is what we have right here, and this results in the expression of our Hamiltonian operator now in terms of the energies of the variables. So what we get as a result is the energy on the x coordinate with that of the wave function. This actually stays the same for our y, plus then we're looking now into our energy on the y and bringing in our wave function with respect to our y, and that shows that we're actually bringing down our x here in terms of the wave function. And we notice now that this now is expressed in terms, which is the left side, in terms of the right side almost, which is what we have right here. So let's see how we can make this right side here to be, you know what, equal to what we have right here. So looking at the right side, what we notice is that if the energy total is actually equal to the energy total on the x coordinate plus our y coordinate, so what that results in is that I can substitute this in here to this particular equation right here, and what that results in is that the E total now becomes EX plus EY applied to our wave function on the x multiplied by the wave function on the y coordinates. So by expansion, what we have, multiplying this by that and multiplying all these both here by the y, what that results in is the expansion, which shows that the EX is acting on our wave function on the x coordinate, and this gives us our y, and y, this is going to be added to the wave function on the y and acting on the wave function on the y, the energy on the y acting on the wave function of the y, and our x right in the right position. So you can see now that the left side is equal to the right side, and this actually proves that we actually showed that this theorem of separability is actually valid for a two variable wave function, well, pretty much using the Schrödinger equation. That's about it for this particular video. Please hit the comment down below, let me hear your thoughts about this and many more. By that way, I can talk to you all later. Stay smart and believe in yourselves.